Okay, great. Good morning, everyone. So first of all, thank you very much to the organizers for the invitation to come speak. And thank you all for coming. I recently started at Yale, but what I'll be talking about today is work I was doing during my PhD at Stanford with my advisor, Ian Johnstone. And the topic of the talk, so we'll be studying a very classical random matrix model. It's just the following. I'm going to look at the model X transpose times T times X, where X has IID entries, they're real, centered at mean 0. And if I scale X by square root of n, then the variance is 1 and the moments are all bounded. And for T, I'm going to assume that it's deterministic and diagonal. The diagonal entries of T are bounded by a constant. And in the applications that I want to consider, which I'll describe in a moment, we want to consider T that's not necessarily positive definite. So T has both positive and negative entries. And the result that I want to explain today is the following. So what's known as that as n and m are both large as they go to infinity, the eigenvalue distribution of this matrix model is approximated by a deterministic Marchenko-Pasteur type law. And the support of this law in general is going to be a union of bounded intervals. And the result that I want to describe, stated informally, is that asymptotically, in this regime, at every regular edge of this support, the extreme eigenvalue has asymptotic GOE Tracy-Widom fluctuations. Okay, so I'll state this more formally later in the talk, and I'll explain also what this word regular means and things like that. Okay, so the outline for the talk is the following. I do want to spend maybe around 10 to 15 minutes talking about actually the statistical motivation for why we're studying this model. In particular because the actual model that we're interested in is more general than the one I just described. And we're interested in this kind of Tracy-Widom result and applications for this more general context, but at the moment I don't know how to prove that. So I wanted to at least explain enough of the statistical motivation to explain where the model comes from and tell you a few things we know in the more general case, but also what some of the challenges might be there. And then for the rest of the talk, I'll focus on the model I just described on the previous slide. So I'll tell you a little bit about the background of this model and a brief history of Tracy-Widom results there. And then the argument of proof that we use to prove this result, so that this conference is called Universality of Random Structures, and the proof is a universality argument. At a high level, it's just based on a Lindeberg swapping idea. And so I'll explain what is the architecture of the swapping argument. And then at the end, I'll try to describe a little bit about the steps that are needed to prove the key estimate behind actually executing this idea. Okay? So let me begin with the statistical motivation of the model we're considering. So the obvious motivation is that when T is a positive definite matrix, this is just the sample covariance model, or it's equivalent to it. And what I mean by this is the following. So let's suppose that I have n IID draws from a multivariate, for simplicity here, let's say normal distribution with covariance T. Then the usual sample covariance matrix is just this matrix here. It's 1 over n times the sum of yi transpose, where the y's are these draws. And I can express this as the square root of T times X transpose times the square root of T, where X has IID Gaussian entries with mean 0 and variance 1 over n, and this is the model I was describing on the previous slide. Okay, so this matrix, of course, has the same eigenvalues as what's usually called its companion matrix, which is X transpose times T times X, up to a set of zeros. And so there's been a lot of study of this model, obviously, in the random matrix theory literature. Okay, so what brought us back to studying this model in our work is actually is a different application where we wanted to consider data that's not independent draws, but instead we wanted to consider a model in which the data have a dependent structure. So on Monday, Professor Bose talked about a time series context in which we might observe a dependent structure. But the model I want to talk about today is a little bit different. And I think the easiest way to explain what this is to just give an example. And the example is the following. So suppose that instead of having independent samples, I have let's say, genetically identical pairs of twins. And I'm measuring traits in these twins, and I'm going to call the number of traits, with an apology to the statistical people in the audience, I'm going to call the number of traits capital N. Okay, and so the reason why we want a model with dependence is because we believe that if I observe traits in two identical twins, then they should be genetically correlated. Right? And so a very simple and classical statistical model that captures this kind of correlation is what's called a one-way layout. So if I write yi1 and yi2 as the traits in the two individuals in the ith twin pair, then the way we're going to model that is as the sum of some shared component alpha I plus two individual residuals, epsilon I1 and epsilon I2. Right? And as a model for the alphas and epsilons, we're going to assume they're random. So the alphas, let's assume for simplicity that they're normal with some covariance sigma A, and the epsilons are also normal with some covariance sigma E. Right? And so the correlation structure of this model arises because of the fact that in each twin pair there's a shared component alpha I here. So in this context, you might interpret these alpha I's as random draws of some shared genetic effects that explain the genetic variation behind these traits that we're studying. And in this kind of a context, is usually not, so we're usually not interested in understanding what is the total covariance of just the Y's, but we're interested in understanding separately what is this covariance sigma A for the genetic effects and what is the covariance sigma E for the environmental errors. Okay, so this is the setup. And so classically for this kind of a model, there is a classical estimate for, let's say, this matrix sigma A. It's analogous to the sample covariance matrix for IID data. It's called the MANOVA estimator, and let me explain what that is. So in this twin design, the way you can construct it is the following. You can, for each twin pair, you can just take the average observation of all of the traits and call that yi bar, and form a sample covariance matrix from that, right? So let me call that sample covariance MSA. It's the mean squares. And you can check that if I take the expectation of this, then what I get is sigma A, which is what I want to estimate, but plus some scaled multiple of the error covariance sigma E, right? Because I haven't removed that error. Okay, and so the way we correct for this scaled multiple of sigma E classically is to look at another sample covariance that's computed from the residuals. So I'm going to take the observation in each individual and subtract its mean in the pair and call that Rij, so J is 1 or 2. And I'm going to define another mean squares matrix, which is a sample covariance object for these residuals. And you can check that on expectation. The expectation of this is just sigma E. Okay? And so the classical MANOVA estimator of sigma A is defined by just subtracting the appropriate multiple of sigma E to make this unbiased for sigma A. All right, so I say it's analogous to the sample covariance matrix because it's an unbiased estimate. It's rotationally equivariant, so if everything's Gaussian, it doesn't matter what coordinate basis I'm in. So it has the same sort of classical properties that you have for the usual sample covariance matrix for IID data. Okay, so what we want to study is a matrix essentially of this form. And this twin design is just a special example of what's a much more general model, which is called a random effects linear model in statistics. And so one way to write down this general model is that I have little n samples of, say, capital N traits. I'm going to call that a data matrix Y. And it's modeled as just a linear sum of contributions from k different random effects. So in the twin design I just discussed, k was equal to 2. You had just the shared genetic effects and the errors, but in general, you might have more than 2. And the random effects, they contribute to this data Y. There's a deterministic, what's called an incidence matrix, U, for each random effect. And then for the random effect itself, we assume there's a random matrix A, which has independent rows. And these rows have, let's say, mean 0 and some covariance sigma. Okay? And in this model, the MANOVA estimate of one of these covariance matrices, sigma R, will take this quadratic looking form. It'll be expressed as Y transpose times B times Y, where B is some estimation matrix that you construct so that on expectation, the average of this is just sigma R. Right? And this particular way of writing the model, and this model itself, in the case of just one trait, in the univariate case, was studied extensively by C.R. Rao in the 1970s. And in particular, Rao was studying the question of, for just one trait, what is the best way of choosing this matrix B? Right? If I want to get, say, minimum variance of this estimate, I mean, there are a lot of choices I can make for B that satisfy this condition, so what is the right way of thinking about that? And as far as I know, so in the high-dimensional settings that I'm going to discuss today, I think this question is completely open still. Okay. And to connect this, just to make sure we're all on the same page, to connect this to the previous twin design, I can write the twin design in this form. The twin design I was discussing was just y equals u1a1 plus a2. So there's no u2, it's the identity. And u here is just this matrix that indicates, which individuals belong to which twin pair. Okay, and the a1 and a2 here will have the IID rows with the two covariances sigma a and sigma e that I described earlier. And so if you want to write down this MANOVA estimator that I described previously in this twin design, it will have this quadratic looking form where this matrix B is the difference between two orthogonal projections. It's a projection onto the column span of this matrix U and onto its orthogonal complement. And so this already shows you why. So this random matrix model that we're interested in studying, it's not necessarily positive definite because of the fact that we're essentially taking a difference in this case, in this special example, of two matrices that are positive definite. Okay, so the general random matrix model that we're interested in studying in this application has the following form. So sigma hat is y transpose times b times y, and y is this linear sum of u and a, so I can write it as this double sum over two indices. And if I factor out the sigma from a, then the matrix model is of this form. It's a double sum with some deterministic matrix on the outside, which represents the square root of the covariances in my model. And then some deterministic matrix X, F on the inside, which is specified by the model design. And then X here is what's random. X is going to have the random, in this case, IID normal entries, but you can assume IID entries of a different distribution. Okay, so this is the model we're interested in studying in the greatest generality. And you can ask a number of questions of statistical relevance in this model. And the questions are related to sort of what kind of structural assumptions we want to make on these underlying population covariance objects, these sigmas in the model. So what I'm going to talk about today is just a very, very special case in which all of these sigmas are the identity, or essentially are proportional to the identity, meaning they represent isotropic noise. And the reason this simplifies things a lot is because if they're just the identity, then they commute with the x, right? So I can pull the sigmas inside, and what I just get is a sum of x transpose f x, essentially, and I can write that in this form, x prime times t times the x, where t is a block matrix with these blocks. Okay, and so this leads back to the model I had in the first slide and why we're studying this model. So I do want to emphasize that so because of the application we're considering, these matrices B and T here in this application are usually not positive definite. Okay. And I can say that, so the reason why I started studying this problem in my PhD is because a quantitative geneticist, Mark Blows, contacted Ian and was asking a question, essentially. You can think about this kind of an assumption that all the sigmas are the identity as a certain statistical null hypothesis, right? That there's no signal in any of the matrices. And Mark wanted to understand whether a hypothesis test of this null hypothesis based on a Tracy-Widom distribution for the largest eigenvalue of this matrix is valid, right? And so it led us down to study this question. Now, to make an argument for why this might be a plausible null model in applications, I can show you a data set that Mark shared with us. So this data is from what's called a mutation accumulation experiment that was done by Mark and his collaborators in the lab. And the data here represent gene expression measurements in fruit flies. And it does correspond to this one-way layout design that I described earlier. And so I won't go into the details of exactly what this experiment was, but basically we have this kind of data matrix Y. And what I'm showing you are the histograms of eigenvalues for 4 different choices of this estimation matrix B. And overlaid on these histograms are a black curve, which is the theoretical prediction of what the bulk eigenvalue distribution should look like based on a Marchenko-Pasteur kind of distribution. If the sigma A's and sigma E's, the covariances truly are just multiples of the identity if they're isotropic. And I think what we see here is that it's actually a reasonable fit to this real data here, except for maybe these outlier eigenvalues here. And so as a null model, it's maybe a plausible null model where the deviations from the null are in terms of these spiked or outlier deviations. So we are interested in the more general context of this model, and I can tell you a few things that we know in this context, and then a lot of things we don't know. So we did some study in the spike setting, where each of these sigmas are now not just the identity, but plus a low-rank perturbation of the identity. And then what we studied were sort of, so when you have these perturbations, you're going to have outlier eigenvalues and eigenvectors. We studied what are the almost sure limits, as well as Gaussian CLTs for the behavior of these outlier eigenvalues and eigenvectors. This is with collaborator Yi-sun at Columbia. And then currently work in progress. So there's a wonderful first-year PhD student, Zhichao Wang, at Texas A&M, and we're working on extending these results to a generalized model where the bulk distribution is not just given by the identity, but the general bulk distribution. And we're also trying to derive what are the almost sure limits of the outlier eigenvalues and eigenvectors. So I won't talk about this result today. There's a very interesting statistical, I think, story behind this result, which is that, so the behavior of outliers in this kind of model, it's not a one-to-one relationship. It's not like if I have one spike eigenvalue in a sigma, then I get one outlier eigenvalue in the sigma hat. There's a complicated dependence of the outliers on the spikes in all of these sigmas. And in particular, where I observe the outliers and the behavior of the eigenvectors, they depend on the alignments between the different eigenvectors and these different sigmas. So it poses some pretty interesting statistical challenges about if I want to actually estimate the true principal components, the true eigenvectors and eigenvalues, how do I actually do that from this? And so we explore this a little bit in our work, but I think there's a lot more that can be done. Yeah. Yeah, okay, yeah. So in this experiment, the number of samples was small. The number of samples was about 80. The number of traits was very large. It was about 3,000. But one thing I didn't mention here is that, so these fits that I'm showing here, we're estimating the dimensionality, the effective number of traits as a statistical parameter. And this was an idea proposed by Patterson, Price, and Reich in the genetics literature. So the effective number of traits that we estimated for this data was about 90. It's not about 3,000. The fits that you're seeing here are suggesting that, roughly some sort of isotropic assumption on a 9-dimensional subspace is reasonably accurate for this data set. That's the claim. Okay. Okay, and then for the model with a general covariance, so if I don't assume anything about these sigmas other than that they're bounded, the results that we have right now, so we have a weak convergence result. So we have a characterization of what is the empirical spectral distribution in this model in terms of a system of fixed point equations in this Stokes transform. And we have this result right now at the level of a weak convergence result. And as part of this work with Zhou right now, we're extending this weak convergence result to a statement that there are no outlier eigenvalues outside the support. Right, okay. So what we're very interested in applications for this model is actually some kind of a Tracy-Widom fluctuation at the edge to facilitate a statistical test of null hypotheses that are more general than just this purely isotropic null hypotheses I mentioned earlier. And this I don't know how to do right now. So if we follow the kind of approach that I'm going to describe today in this talk, then it seems like the first step that we might need to do that is some kind of an optimal local law for the convergence of the eigenvalue distribution of this kind of matrix to this mu naught, which I currently don't have. I can say that this first work is the only one we did analytically. Everything else we did using sort of more generic free probability approaches. So I don't quite know using that kind of technique how to get to this kind of an optimal local law at the edge. Okay. Okay, so this is what I want to say about the general model. I hope that maybe I can convince some of you in this audience to think about this model and this problem. But so for the rest of the talk, I'll focus on the more specific case of just the isotropic covariances, which leads us to this much simpler model, which is just x transpose times t times x. Okay, so this is the notation I'm going to use in the talk. T will be diagonal, we'll suppose. I'll call its diagonal entries T1 through Tm, and they're bounded. So they're not necessarily positive or negative, but they're bounded. Okay, so this is the model that was studied by Marchenko and Pasteur. And so what we know about his bulk eigenvalue distribution is that there's a certain fixed point equation, which is the one I wrote here. So Z naught M is the functional inverse of the Stokes transform of this model. And what's known is that, so this equation, Z equals Z naught M, has a unique root for every Z in the upper half complex plane, a unique root M. And this root will define the Stokes transform of a measure mu naught, which approximates the eigenvalue distribution of the sigma hat. Right? So this kind of result is due to Marchenko and Pasteur. And the particular expression of the fixed point equation in this form, I think, is due to Silverstein in 95. Okay, and one just sort of point maybe I should clarify or emphasize is that this distribution mu naught is a deterministic distribution. We're going to define it in terms of the finite n empirical distribution of the entries of T and the finite n ratio n over m, right? So it's not some limiting object. You can translate the results that we have into some kind of limiting object if you want, if you assume that the convergence to this limit is fast enough. Okay, so what we're interested in is Tracy-Widom fluctuations at the edges for this model. There's a long history of Tracy-Widom results for this kind of model, starting with the case where T is just the identity, right? So we're just looking at a white sample covariance matrix X transpose times X. The first results were in the Gaussian cases by Johansson and Johnstone, and then there were a number of universality results that extended this to general distributions for X. In a separate line of work, there was a study about Tracy-Widom in this model for T, not the identity, but more general T. And this line of work started with the assumption that X is complex Gaussian. So if you assume X is complex Gaussian, then there's the HCI-Z integral formula for the joint eigenvalue distribution in this model. And this led to a number of papers, starting with Bike, Benarus, and Pache, which established Tracy-Widom fluctuations at first the largest edge and then all edges of the spectrum for T with spike structure or T with general structure. And I want to emphasize in particular a work of Hachem, Hardy, and Najim, which considered a general T and showed Tracy-Widom GUE fluctuations at all the regular edges of this model. And this is the sort of complex Gaussian analog of the result that I want to talk about today. Right? So in the complex Gaussian case, you can get this kind of result from an explicit formula for the joint eigenvalue distribution. Okay. So for the case where X is real, there are a number of arguments in various settings, and these arguments are all based on universality techniques. So the first work that I know of is this one by Farrell and Pache, which considered a spike structure for T. So all the entries of T are equal to 1, except for a few large ones. And this was done using a moment method. And then there was a paper by Lee and Schnelli, which studied a general T and the largest eigenvalue for a general T. And it's this technique of Lee and Schnelli that we generalize in order to get to our result at every edge. Right? And so these are resolvement-based techniques, and I'll describe what the technique is later. And so these are all assuming that T is diagonal. There are universality results in X that have been established for this model by now as well. First by Balpan-Zhou at the largest edge, and then by Knowles and Yin at all regular edges. And so what this means is that our result, at least for T positive definite, we can remove the assumption that T is diagonal, and that, we can remove the assumption that T is diagonal. I think that these universality results will carry over to T with negative eigenvalues as well, with basically the same proof. But I won't talk about that. Okay. So other questions about what I'm going to talk about? Okay. So in order to state our result a little bit more precisely and tell you what is the meaning of this word regular, I need to tell you a few things about this model. So what's known is that, so this Marchenko-Pasteur measure, this deterministic measure, many properties of its density and support can be read off from this function z naught of m that I stated earlier. So this result is due to Silverstein and Choi in 95. It says that every edge of the support of this measure corresponds to a local minimum or maximum of this function z naught of m, right? Where z naught of some value m star is the value at that edge. And I'll show you a picture in a little bit. And so if this local minimum or maximum is at infinity, meaning we identify infinity with negative infinity, and so if there's a local minimum or maximum at infinity, then what you get is a hard edge at 0. And the hard edge at 0, so the density will blow up on one side of 0, and it'll be 0 on the other side of 0. But otherwise, you'll get a soft edge, and that soft edge will have a square root decay. Okay, and the scaling of the square root decay is associated with the inverse of the curvature of this function z naught of m at this value m star. And so here's a picture explaining what this result is saying. So here's a histogram of eigenvalues of the matrix from this model. For this particular choice of T, there are 4 edges of the spectrum, 1, 2, 3, 4. And if you plot this rational function z naught of m on the real line, what you get is this function over there. It has a number of poles, but what we're interested in are the critical points, so the local minima and maxima of this function, and you'll see that there are 4 of them, and each one of these corresponds to one of the edges, right? So I don't know if I have a pointer. I'm not going to try to attempt. There are 4 of these extrema, and each extremum, the vertical axis value is exactly the value at that edge. And then the curvature of this function at that critical point is going to give you how steeply how steep is the square root decay of the density at that edge, right? So at this edge here, for example, where you have a very sharp square root decay, you have a very small curvature, so it corresponds to this critical point right here with a very small curvature. Okay. So this is an example where there's no hard edge. I can show you an example where there is a hard edge. So this is an example where n equals m in dimensionality of this model. And so what you see in this function z naught of m is there is a local minimum at infinity in this curve. And what that local minimum corresponds to is this hard edge at 0 in this model. So the density blows up, in this case, on the left side of 0, and it's 0 on the right side of 0. Okay, so what we're gonna study in our work is only the soft edges. We're not gonna study the hard edge. Okay, so what do I mean by this word regular for an edge? So we're gonna define this word regularity in terms of this function z naught of m. So we're gonna say that an edge is regular if the corresponding m star value is bounded away from infinity, if the curvature is bounded away from 0, and if the m star value is also bounded away from all the poles of this function z naught. And if we want to quantify these bounds, we're going to throw in a constant tau here and say it's tau regular, otherwise I'll just say it's regular. And I think a more interpretable interpretation of what this regularity means is that, so it implies the following. It implies that as n and m go to infinity, this edge does not converge to a hard edge at 0, so it remains soft. The scale of the square root decay at that edge remains of constant order asymptotically, and the edge has constant separation from all the other edges. So it doesn't close and become some sort of cusp, and it doesn't correspond to an interval of support that shrinks to 0. Okay? And this notion of regularity, the first sort of definition like this was introduced in this work by Al-Kharoui in 2007, where he introduced a condition like this for the largest edge. And then what I'm stating here, I think, is a pretty natural generalization of some similar definitions that were assumed for positive definite T previously. So I'm not imposing an assumption on T. I'm assuming that T is bounded. And then this measure mu naught is going to be an n-dependent measure. So it's defined in terms of the empirical distribution of the entries of T and this ratio n over n. So it can change as n changes. It doesn't, yeah. It's really just for convenience. Because at the end, you know, the comparison between the actual eigenvalue distribution and some deterministic distribution is with this one. It's with the n-dependent one. And if you assume that T goes, you know, T converges to something in the limit, then you need to impose some condition about the rate of that convergence. Yeah, so I think this is the right object to compare it to. Okay, so our result is the following. I can state it more formally now. If n and m go to infinity proportionally in this sense, and I look at any regular edge of this distribution mu naught, then if it's a right edge and I look in some small interval around this mu naught, then the largest eigenvalue in this interval will fluctuate with a GOE Tracy-Widom fluctuation. And correspondingly, if I look at any left edge, and I look at a small interval around the left edge, that will also fluctuate with the GOE Tracy-Widom fluctuation. Okay. And the scale, so the scaling constant of this fluctuation is on the n to the 2/3 scale, as we would expect in these kinds of models. And the specific scale constant is this gamma that describes this sharpness of the square root decay at the edge. Yeah, over. Okay, yeah, so the matrix here, the matrix is real. We're not assuming it's Gaussian necessarily. I'm just assuming T is diagonal. Because the kinds of arguments that we're using, we're not going to use any Gaussian property. So they actually just they work for general distributions of X with bounded moments. And the place where some kind of Gaussianity assumption is being used is the fact that we're assuming T is diagonal. So if you want to consider a non-diagonal T, you can kind of diagonalize it if X is Gaussian. But otherwise, you need some other universality result to get that. Okay. Okay, so that's the result I want to explain. And so I want to explain for the rest of this talk at a high level what is the method by which we prove this. And the method is a universality argument using some Lindenberg swapping idea. Okay, so the idea is this. We want to study this model, and we have this matrix T, and the swapping idea is we're going to take every entry of T and swap it out with something else, right? So we're going to swap the diagonal entries of T one at a time. And so I can state that in the form of a following lemma. So there's a sequence of diagonal matrices, T0, T1, et cetera, TL. We're going to make a total number of swaps that's order n, where n is the sort of the dimensionality of T, right? And so every time I swap a diagonal entry of T, this measure mu naught changes a little bit. This Marchenko-Pasteur measure that's defined by T is going to change a little bit, and so the edge is going to move a little bit. And so corresponding to each of these swaps, I'm going to track that edge. So I'm going to call E star 0 through E star L, you know, some edge of this Marchenko-Pasteur measure. Okay, so the conditions I want for the swap are the following. So at the very beginning, I want to start with what I'm interested in, which is the particular t and e star that I'm interested in. And for each of these things in the sequence, I'm just swapping one entry. So I'm removing one entry of t and swapping it with something else. Okay, that's fine. And the content of the lemma is the following, that there always exists so if I started with a regular edge, then there always exists a sequence of order n swaps that sort of preserve this edge. So I can keep tracking this edge. It doesn't disappear along the sequence of swaps. It remains regular, maybe with some different constant tau prime. And furthermore, the location of the edge for each of these swaps is only going to change by order 1 over n. And if I recall this value m star, which is this local minimum or maximum corresponding to that edge, I can guarantee that also changes by only order 1 over n. Okay? And then finally, at the very end of the sequence, what I want is that every diagonal entry of t is one of two values. It's either 0 or it's some other value, which I'm going to call little t. Okay, so the content of this lemma is that there exists a sequence of these swaps. And to show you this, I created just a quick animation. So suppose that, so this is one of the two examples I showed earlier. This black curve is the bulk law, and suppose that we're trying to prove something like Tracy-Widom fluctuations at this edge. And so the underlying t for this model, I think, has 3 distinct values. There's one distinct value corresponding to this bulk component here, and 2 values corresponding to this bulk component here. And so what you're going to see is I'm going to slowly swap out these values for values over here, and then slowly swap these 2 values to just become 1 value. Okay, so let me see if I can get this to play. Yeah, okay. And so you can see that as the swaps occur, you'll have a deformation of this distribution. And that for each swap, the edge moves a little bit, and we're just going to track this edge. Right? So the thing that's in red is just, here I can play it. Okay, it's on red. So we track this edge along the sequence of swaps. Okay, and in this case, I'm just swapping all the values for some constant, I believe, positive value, t greater than 0 here at the end. Okay? I can show you the second example. So in this other example where I had a hard edge here, I can show you the sequence of swaps. So for this example, there were 2 distinct values along the diagonal of t, 1 positive and 1 negative. And so in this case, I can't swap all of them for the positive one, because what would happen to this edge is that it would converge to a hard edge at 0, which would not have Tracy-Widom fluctuations. And so our idea is you can instead swap them out for 0. Right? Okay, so in this case, we're just going to swap all the negative entries out for 0, and this is what happens along the sequence of swaps. You'll see the left bulk component disappear, and then the right bulk component will become a standard Marchenko-Pasteur law, and we're going to track this lower edge there. This vertical line is because at the end of the day, we're swapping to a setting where the matrix is singular. Okay, so this is the content of that lemma. That swapping lemma, that the existence of a sequence of swaps like this is a fairly elementary statement. You can, we give an explicit construction for a sequence of swaps in our work, but I don't think it's unique, and you can do it in a number of ways. Okay, so the main content of the work is the following. So we want to be able to understand what happens to the extremal eigenvalue at this edge along every swap, right? So let me introduce some notation. So instead of keeping these superscript indices, I'm just going to call the quantity before any swap t and e star, and the quantity after any swap t check and e check star. So anything with a check is the one after the swap, and anything without a check is the one before the swap. And what I want to do is so I want to look at the extreme eigenvalue at the edge I'm interested in. It's random, so let lambda be the eigenvalue before the swap, and lambda check be the one after the swap. So it's extreme eigenvalue near e star and e check star. And the main quantitative estimate that we need to show is the following, right? So we show that if I look at the deviation from lambda to the edge e star, scaled appropriately by gamma n to the 2/3, that deviation for any fixed x, if I take that CDF probability and subtract the probability after the swap, so I look at lambda check minus e check star and then scaled by gamma check, that this change in probability is asymptotically smaller than order 1 over n. Okay, and that's enough to get what we want, because the total number of swaps that we're making is order n. Right? So if we make order n swaps and this probability changes by less than 1 over n, then what that means is that the fluctuations at the very start of the sequence, lambda naught, that has to be the same as the fluctuations at the end of the sequence, okay, with the appropriate center in scaling. And then at the end of the sequence, we have a matrix where all the diagonal entries are just 0 or t. And so what this matrix is just some scaled multiple of a white sample covariance matrix, and you can check that the dimensions are still okay. And because we know that there's a GOE Tracy-Widom limit at both the upper and lower edge for this white kind of a sample covariance matrix, we have our result. Okay, so most of the work goes into proving this estimate. Okay. Are there any questions? So in the rest of this talk, what I want to do is maybe describe some of the high-level steps behind the proof of this estimate. And so, so before I do that, I want to say, so this entire idea of doing this comparison argument, as well as a number of the ideas in how to do this estimate are due to this paper by Lee and Schnelli in 2016. So what Lee and Schnelli considered, so they studied just the largest eigenvalue of a matrix like this, and instead of considering a Lindenberg sequence, what they considered is a continuous flow. And in this continuous flow, it's some sort of Ornstein-Uhlenbeck looking kind of thing where they took this equation here. So at L equals 0, you start with the matrix you want. At L equals infinity, you end with the identity. And L here is the flow parameter. And what they did was to track the upper edge along this flow. Okay, so this particular idea won't suffice for the kind of model that we want to study for two reasons. One is that we're interested in applications where T has both positive and negative eigenvalues. And if you look at the way this flow is defined, this quantity inside, some eigenvalue will hit 0 along the flow, and so it's not really a continuous flow if T starts with negative eigenvalues. The eigenvalue is going to go off to negative infinity and then somehow wrap back around from positive infinity to 1. Okay, so I think this is more of a technical point. The second, I think, perhaps more real point is that if you want to study interior edges of the support, you can't really use this kind of continuous flow, I think. Because of the problem that along this flow, all the intervals of support will just merge into each other. Right, so as I do this flow, instead of this discrete swapping thing where one interval of support disappears and the other one appears, they're going to all mush together. And let me show you a video of this. So before I do that, I want to say that so the Lindenberg argument we're doing is different, but the analysis behind proving that kind of technical estimate I just said uses a lot of the ideas in Lee and Schnelli. Okay. So to explain what I mean by the intervals merging together, so this is an example where T is positive definite, so you can run the Lee-Schnelli flow, and I can run it for you. And what you're going to see is that as we flow all of these eigenvalues together, these two intervals of support will merge together, and if we're going to lose the two interior edges of the spectrum. Let me play this for you. So at some point, the intervals of support merge, we lose that interior edge, and this doesn't provide a way of accessing, the fluctuations at that interior edge when we started, if at the end that edge is not there anymore. Okay, so somehow using this discrete Lindenberg idea, we can make this larger interval of support entirely disappear while preserving this edge that we were interested in. Okay, fine. So now I want to finish by explaining some components of this estimate that I described earlier. Okay. Okay, so let's see. So the first thing I want to say is that I lied a little bit to you in the sense that what we're going to consider is not an exact Lindenberg swapping sequence. And the reason for that is for convenience of how we want to write down this argument, we're going to rescale the T's so that the scale of the Tracy-Widom fluctuation doesn't change along the sequence. So we had this parameter gamma that described the scale, and by rescaling T, I can make sure that all of these gammas are equal to 1. Okay, and so if I do this rescaling, then what happens is that before and after each swap, I don't just have one entry of T changing. Instead, what I get is that one entry of T changes by order 1. All the other entries of T you can show change by order 1 over n. And so the total change in absolute values of all the entries of T is bounded by a constant. And that's the only property that we're going to need. And we can still ensure that the edge only changes by order 1 over n. And this associated m star value still only changes by order 1 over n. And the scales are fixed at 1. Okay? And so I'm going to call the matrix before and after the swap here T check, and then the edge E star check. I'm going to call this a swappable pair if it satisfies these conditions. Okay, and the kind of estimate that we want is that whenever we have a swappable pair, then the fluctuation probability at that edge is essentially the same. Okay, and the way we study that probability is to use this resolvent approximation idea by Ayyer, Xiao, and Yin. And so let Mn be the Stieltjes transform of this distribution, which is 1 over n times the trace of the resolvent. And because the Stieltjes transform, so you can think about it as the convolution of the eigenvalue density of this matrix with this sort of Cauchy distribution or Poisson kernel. And so if we take the imaginary part of the Stoichkos transform to be less than n to the negative 2/3, which is the scale at which we believe this eigenvalue fluctuates, then we can make an approximation to the indicator function that an eigenvalue is in some particular interval at the end of the negative 2/3 scale. Okay, so what I mean by this is the following. We're going to fix some imaginary part, which is a little bit smaller than n to the negative 2/3. And then if we want to look at the number of eigenvalues of this matrix that belong to some interval, let's say E star plus S1 to S2, where S1 and S2 are both approximately on the n to the negative 2/3 scale, then this number of eigenvalues I can approximate as 1 over pi times this quantity x, where x is going to be the integral of the imaginary part of the Stoichkos transform. Okay, so this is some resolvent approximation for the discrete number of eigenvalues in this interval. And then what I want to study is the probability that there are no eigenvalues in some such interval. If I can understand what is the probability there are no eigenvalues in any interval like this, then I understand the distribution of the extremal eigenvalue. Okay, and so if I want to approximate what is the probability that there are no intervals belonging to this, what I can do is to take a smooth approximation to the indicator function that's going to be 1 at 0 and 0 everywhere else. So I'm going to smooth this indicator function and then study the expectation of this smooth indicator function k of this quantity x, right? So we have a smooth approximation to this discrete object that we want, and this idea is in this rigidity of eigenvalues paper by Ayyer. Okay, so the actual quantity that we want to control on the swaps is then this expectation, the expectation of this smooth function k of this quantity x. So what I can do is define the analogous quantity x check after the swap. It just has this new edge e check star, the Stoichkos transform of this new matrix with the t check. And then what I want to show, the key lemma, the key estimate that we want to show is that the difference between the expectation of k of x and k of x check is much smaller than 1 over n, and the precise bound that we prove is n to the negative 4/3 plus an order epsilon quantity, where epsilon was a small parameter. Okay, so this is the main estimate that we want to do. And the reason we make the smooth approximation and we can do this kind of estimate is because now I can study these quantities in terms of the resolvent of the matrix. Okay. So we're going to define a linearized resolvent. The resolvent I want to look at is this linearization of this model. Let me call this resolvent G. And let me call the resolvent after the swap G check. So G check is going to be defined with T check instead of T. Then in this formula for x, what I have is n times the Stoichkos transform, which is the sum of diagonal entries of the upper block of G. Right, so I'm going to index G. The first 1 through n coordinates I'll index by Roman letters, and the last 1 through m coordinates I'll index by these Greek letters. And so this x that we're looking at, I can write in terms of the sum over indices I of these diagonal elements of the resolvent. Okay. So what I'm interested in studying, before I say that, okay, so a technical tool that we're going to use extensively in this proof is coming from the local law that's known for this model. And if I apply the local law near this sort of regular edge of the spectrum, what it tells me is that the diagonal entries of this generalized resolvent, don't worry about the scaling by T alpha. So the diagonal entries of this generalized resolvent are of order 1. And the off-diagonal entries are roughly of order n to the negative 1/3. So the xi here is n to the negative 1/3 plus some small epsilon thing. And so this was known for positive definite T. There's small generalizations that you can do to establish this for T having negative entries as well. Okay, so this gives us some sort of entry-wise control of this resolvent that we want to study. And so the steps of the proof are the following. So what I want to bound is the expectation of the difference between k of x and k of x check. Right? And the way we're going to bound this difference is to use a sort of Taylor series kind of representation of this difference. I can write this difference as the integral from 0 to 1 of d by d lambda of k of x lambda, where x lambda is just a linear interpolation between x and x check. Okay, so I want to emphasize this is not the same thing as interpolating continuously between t and t check. Right? We have these two quantities here, and I just introduce artificially this linear interpolation. And the reason I do this is because then I can write d by d lambda of this as the derivative of k times just the difference between x and x check. Right? So it moves the difference outside of these k's. Okay. So here, x minus x check, because of this resolvement expression for x and x check, what I can write this as is the sum of diagonal entries of the imaginary part of the differences between these two resolvents, GII and G check II. Right? So I have these two different resolvent matrices. Here, G is evaluated at E star plus Y plus I eta, and this G check is evaluated at a slightly different location, E check star plus Y plus I eta. Okay? And these both depend implicitly on Y. Okay, so this is step one. So once I get this difference of these two resolvents, then what I can just do is to use the resolvent identity. So if I have A inverse minus B, I have this resolvent identity. And so GII minus G check II, I can use this identity to write it in terms of resolvent entry. So if I go back to the definition of this linearized resolvent, what's different between G and G check is two things. One is that T is replaced by T check. And the second is that this argument Z I'm evaluating, and one of them there's an E star, and the other one there's an E star check, because the edge moves a little bit. And so if I apply this resolvent identity, I claim that what I get is some term that involves the difference between the edges, E star minus E star check, and then some term that involves the difference between the T's, which is T minus T check, and we get this kind of a formula. Okay? And what this already shows us is a following crude bound for what we want, right? So what I know for the swappable pair is that the edge doesn't move very much. The edge moves by order 1 over n. And the T's don't move by very much. The total movement of all the T's is order 1. And so if I just plug in these bounds naively, and then I use the local laws to get bounds on these off-diagonal entries of G, then the kind of bound that I get is enough to show that the difference between x and x check is of order n to the negative 1/3. And therefore, the difference between the k's, using this sort of Taylor approximation kind of thing, is also of order n to the negative 1/3. And what we're off by here is a factor of 1 over n. Our goal is to show it's n to the negative 4/3. And if I just apply this sort of naive bound here, what I get is n to the negative 1/3. Okay, and so the idea of getting a stronger bound here is that there are certain cancellations between these two terms, right? So each of these terms individually is of the size xi squared, which is n negative 2/3, but there's a cancellation between these two terms, and this is the same idea as in Linearized jelly. And we want to exploit this cancellation to get a much better bound on the difference between these two things. Okay, so let me try to explain a little bit where this cancellation comes from. The first place where it comes from is that we have an explicit description of the difference of this edge location. So E star, as you recall, so the value of the edge is exactly this rational function z naught at this parameter m star. And z naught has this explicit form. Right? So I can write z naught explicitly in terms of m star, introduce some s alpha, which depends on m star. And I can write explicitly what is the difference between E star and E check star. And there's a leading term that is of order 1 over n. It's the difference in the edges. And the remainder term here is of order 1 over n squared. And this remainder term I can drop because it gives me that extra factor of 1 over n that I want. Right? So I can plug in this E star minus E star check, and so only the leading term here, and get that the resolvent difference that I want, an entry of this resolvent difference, has this expression here, where the remainder is negligible. It's of the order that I want to establish. Okay? So this is the first step. And now I have everything in terms of the resolvents here. And the final sort of key step of the estimate, so what are we actually interested in? We're interested in the sum over I of this quantity. This quantity depends explicitly, it depends implicitly on y, the spectral argument, so I want to integrate over y, the imaginary part of this, and then multiply by some k of x lambda, right? So I'm going to define two terms that essentially correspond to this first term here and the second term here with everything included. So I have an integral d lambda, sum over these alphas of the imaginary part of the expectation, k prime of x lambda, and then this first term, and then the second term. So these are the two terms, and the bulk of the proof is that there's a very tedious calculation that we do. The ingredients of the calculation are just a Taylor expansion of this function k, together with your complement identities for these two resolvents. From this calculation, we can show that the difference between these two quantities has two terms. One term is of order n to the negative 5/3, essentially, which is small enough for what we want. And then curiously, we get a term that's of a larger order than what we want, but it's actually going to cancel. So there's an additional term here that has a certain symmetry, right? So it's an integral with respect to some spectral argument y tilde of this function yi y tilde, where we have the sign symmetry. Okay. Okay, so I can't really explain any part of this calculation in this talk. This calculation generalizes a calculation in the Lee-Schnelli paper. So in the Lee-Schnelli paper, because they considered a continuous flow, what they needed to establish was a certain differential version of this identity. And what I mean by differential version is that there's no discrete difference between t and t check. Instead, you just have the derivative of t along this flow parameter. And then there's no difference between the g and g check, and no difference between s and s check, et cetera. So there's just one g, and then there's just one s. And then this x lambda here was this linear interpolation lambda times x plus 1 minus lambda times x check. There's also no difference between x and x check there, so there's no integral over lambda. All right, so in their bound, this integral over lambda is not there. This is just k prime of x, and then you have all the check quantities are the same as the unchecked quantities with a continuous time derivative, and they were able to establish essentially this kind of a bound without this term here. Right, so they get this order xi to the fifth bound, and we show that if you do this discrete kind of argument and end-to-end bound, you can get a similar bound with this additional term that ends up canceling. Okay, so if you believe me for this step, then we're done. Because what we want at the end of the day, so we want to bound the difference between the expectation of k of x and k of x check. And so this is just the sum over I, integral over y of these two terms, 1 and 2, that I wrote on the previous slide. And because of the symmetry of this term in y and y tilde, when I integrate this over y, it actually vanishes for a reason that I honestly don't completely understand. It just popped out of the calculation. And then the other term is of the order that we want. So the other term is xi to the fifth, which is n to the negative 1/3. The number of indices I'm summing over is n. The range of integration is n to the negative 2/3. And if you put everything together, you get n to the negative 4/3. And that concludes the proof. Okay, so that's all I wanted to say about this topic. The main reference for this, so we have a paper on arXiv where you can find more details, and then some of the more relevant references that I mentioned are here. Thank you very much.